Hi all, in this short video I am going to discuss how to graph the derivative of a function. So we're going to start with what appears to be an upward facing quadratic f of x, and f of x is always concave up, but you can see that at times the function is above. On this interval the function is above the x-axis, and on this interval it's also above the x-axis, and on this interval it's below the x-axis. But most importantly, if we're plotting f prime, keep in mind that f prime of x, which I'll plot in red, f prime of x is all about the slope of the function at a variety of points in this case. So I'm going to select a series of points, as I've done in the past, and I'm going to sketch the derivative, the values of the derivative at that series of points. So if I start with the slope at this point, we can see that it's quite negative. The slope at this point is a little bit less negative. The slope at this point is a little bit less negative. And it's still negative, but a little bit less negative. Now let's consider, maybe even go here, and now let's consider this variety of points and where the derivative values would actually fall. So the outputs were the values of the derivative. Well, here we're very negative. We should be down here somewhere. A little bit less negative indicates that maybe we are that our output should be a little bit less negative. On the derivative function, less negative, less negative, less negative, and right here we can see that the derivative is actually 0. So if we look at the derivative on that interval, it should look something like this. Now notice I don't have an equation for f of x. I don't have a formula or a function for f of x. I just have a picture. But if this is what f of x looks like, then f prime of x would look something like this. Remember that when the function is decreasing, we expect the derivative, we know that the derivative is going to be negative. Now, this unique value right here, which happens to fall on the y-axis, the function is going to go from decreasing and change over to increasing. So on this interval, we know that f prime of x should be positive. If f of x increases, then f prime of x is positive. But right here, at this ordered pair on f of x, the derivative is actually 0. So in that instance, we would hit the origin. Now, the function itself is increasing just a little bit here, a little more, and our rate of increase itself is picking up. If you think of the slopes of these tangent lines to the curve, and so here we line it up, we're a little bit positive, we're a little more positive, I'm graphing the derivative, a little more positive, and that pattern continues. And so the rest of the derivative function here would look like this. Now we've discussed in class, but I do want to remind you that let's just say that f of x is a quadratic. If f of x is a quadratic, then f prime of x would be linear, and we can see that that happens here. Let's jump over to g of x. Now I'm going to pick up the pace a little bit, so I'm going to select a variety of points, and I'm going to consider the slope of the tangent lines at a variety of points to the curve. Okay, so plotting g prime of x, the function is increasing quite a bit here, which means that our derivative should be quite positive. Increasing a little less at a lesser rate, we're increasing at a lesser rate, increasing at a lesser rate, but notice that the derivative here should still be positive. It should still be slightly positive here, and here finally we hit 0. Okay, here we hit 0. So it looks like g of x could also be quadratic, and so we would say that g prime of x could also be linear. Here's g prime of x, as in the previous example. However, in this case, on this interval, we know that g prime should be above the x-axis. It should be positive because g of x on that interval, g of x is increasing. And again, right here, the derivative is 0. The slope of the tangent line of the curve is 0, so that should line up. Now, we've got g prime is slightly negative. The slope of g is slightly negative, and therefore the derivative is slightly negative, and that pattern continues as far as the derivative becomes more and more negative, and g of x is decreasing that whole time. All right, let's look at h of x. So h of x has a couple of changes in direction. Again, I'm very positive. My derivative is very positive, and it's going to get a little bit less positive, and a little less positive, and a little less positive, until eventually it hits 0 right here. So the derivative right there is 0. Now the other point where the derivative is 0 is over here. So the derivative is going to intersect the x-axis of both of those points. Now I want to focus on this interval for a moment. So focus with me right here. And we're going to look for, I want to show you something maybe subtle, but it's going to continue to play a more important role as we progress through the calculus course. Right here, at that point, is where h of x reaches its maximum rate of decrease. So if I'm sketching these tangent lines, you can see that the derivative is a little bit negative, the slope's a little negative, it's getting a little more negative, it reaches its maximum rate of decrease here, and then it starts to, its rate of decrease goes back and approaches 0. And again, the derivative is 0 right here. Well, if that's true, which it is, then we should expect the derivative to reach its minimum value right there, because that's where it is most negative. And at these ordered pairs, we are slightly negative, getting a little more negative, and then here we're getting a little bit less negative, a little bit less negative, and finally we're back to 0. Now on this interval here, the function is increasing the whole time, so we expect h prime to be positive. It's a little bit positive, a little more positive, a little more positive, and the pattern continues. And if we put all this together, then h prime of x should look something like this. Again, some key points that I want to focus on. The derivative is 0 right here, so we should expect the derivative to intersect the x-axis. The derivative is 0 right here. Again, it intersects the x-axis. The derivative reaches its maximum, it reaches its largest rate of decrease right here, and so there should be a local minimum in this case on h prime of x. Notice again that h of x is appears to be a cubic. We're going to call it a cubic, and so h prime of x is one family below that. With respect to polynomials, we're saying that h prime of x is a quadratic. Just as in the previous two examples, h of x was a quadratic, h prime of x then was linear. All right, if we take a look at this example, we'll call it j of x. Doesn't look like I named it. J of x. We want to sketch again the derivative, so let's talk through this. The function is always, j of x is always increasing. And because it's always increasing, we know that j prime of x will always be above the x-axis. It's going to be above the x-axis. Again, because j of x is always increasing. So with respect to our rates of change, at this input, if we line that up, okay, our derivative is quite positive. At this input, our derivative, the slope of that line, is a little bit less positive. We're a little bit less positive, but we're still positive. A little bit less positive, but still positive. And that rate is, the function is always increasing, so that the rates are going to always be positive, but notice they are approaching the x-axis. And so j prime of x, just a sketch, we don't have an equation, we don't have a function for j of x, so we're not going to find a function for j prime, but j prime of x would look like that. And back to our review of limits, we would say that the limit as x goes to infinity, for example, of j prime of x is 0. We could say that the limit as x goes to negative infinity of j prime of x is positive infinity. Okay, I've got 4 more examples we'll talk about, and then we'll call it. Here we've got k of x. You could argue k of x has 1, 2, 3 changes of direction. You could argue that it's a 4th degree polynomial, and for the sake of that, let's just go ahead and say it's a 4th degree, so we would expect k prime to be a 3rd degree. K prime should take on the cubic form, and we'll see that in just a moment. I am going to go ahead, and this time I'm going to say, all right, where's the derivative 0? The derivative is 0 here, here at this x value, and at this x value. Think about why. The slope of the tangent line of the curve is 0 at all 3 of those points. Now, on this interval, k is decreasing. So on that interval, we should expect k prime to be negative. And think about the rates. The slope's very negative, and it's getting less negative and approaching 0. And so k prime would look something like this on that interval. On this interval here, k is increasing the whole time. Again, notice from the previous example, the maximum rate of increase is going to occur right here, if you think about it, which means that we would expect we know that k prime is going to have a local max right there. So again, the slope's a little positive, a little more positive, reaches its maximum increasing rate, a little less positive, and a little less positive. And so the derivative is going to look like that on that interval. Okay. The function itself is decreasing on this whole interval, so we expect the derivative to be negative. Once again, you have your maximum rate of decrease right here. And so the derivative itself would look, it would reach a local min there, and it would look something like that. And last but not least, we're increasing on this whole interval, and our rate of increase itself is also going up. It's increasing. And so we would expect that, we would expect that the derivative would look like this. Okay, that's not meant to be linear. It's not meant to be linear. And so we have a cubic derivative. If k of x is a fourth degree, then k prime should be a cubic. L of x. L of x looks like it could potentially be the function negative 1 over x, possibly. But we're going to sketch the derivative most importantly. And so think of your slopes. They're a little bit positive, okay, getting more and more and more and more positive. And so if you think about it, this piece right here, the derivative should be slightly positive and getting more positive, and that piece of the derivative is actually going to take on the same shape as the original function. On this side, over in quadrant, remember you got quadrant 1, 2, 3, and 4. So over here in quadrant 4, the function is increasing rapidly, which means the derivative is quite positive. It's increasing at a slightly lower rate, but it's still increasing, and that rate of increase is going to approach 0, but the function is always increasing, and so once again, the derivative will always be positive, and so this side of the derivative would take on this shape. We've got L prime of x. P of x. Well, P of x is intended to be some form of the absolute value function, but what I want you to notice is that both of these pieces are linear. It's really a piecewise function. You've got two linear pieces, okay? And so if it's linear, then the slope is always the same. This entire time, the function is decreasing at the exact same rate of change. So if I'm sketching the derivative, I would expect that that is going to be negative, and it's always the same value, so we should have a horizontal line, okay? Now, we'll talk more later in the course about why, but right here the derivative does not exist at that sharp corner. So I've got an open circle here. On this portion of P of x, we're increasing at a constant rate the whole time. That's also linear. However, because we're increasing, we would expect the derivative to be positive, and it's always going to have the same value, okay, in this case. So if I sketch that, I'm going to jump above the x-axis and have a horizontal line going in that direction. And so there, P prime of x is also piecewise. P of x was a piecewise function. P prime of x is also a piecewise function. Both pieces are horizontal lines. Again, the derivative does not exist there. We'll talk about that more later in the course. Last but not least, Q of x. Q of x is an interesting function in that you have a local minimum on the function here. We expect the derivative to be 0, but in this case, you're quite negative, getting a little bit less negative as you approach that value, and so we are line it up. We are quite negative, a little less negative, a little less negative, a little less negative, and so the derivative itself would look something like that. It's negative in Q prime of x on that interval is negative because Q of x is decreasing. Okay, I want to focus back here for just a moment. We are going to slightly increase. Our rate of increase appears to pick up, and then it appears to die back down again, but we're still increasing that whole time, approaching what looks like a horizontal asymptote. And so our maximum rate of increase looks like it happens right about there, which means that the derivative function should have a maximum right there, a relative maximum. So we're going to reach up, we're going to hit that peak, and then we're going to start to come back down and level off because the slope is going to approach 0. So Q prime of x would actually look something like this. Okay, that's all I have. I hope that helps your understanding of graphing the derivative of an original function.